Something like that. Okay. I guess we'll get started in just one more minute. All right, so if I remember correctly, last time we covered Marlin, which is a snark with a universal trusted setup. So that setup is called Powers of Tau. And that setup is coming in purely because Marlin uses KZG polynomial commitments. So if you replaced KZG polynomial commitments with another polynomial commitment scheme, you could get rid of the trusted setup in Marlin, but then you would lose kind of its most attractive property, which is its verification costs. So it has constant size proofs, meaning the proofs consist of some constant number of group elements. I think that number is on the order of, it's about 12. That's not an exact number. I'd have to double check. So it uses KZG polynomial commitments because the commitment size for KZG polynomial commitments is one group element, and the size of the evaluation proofs, I think, are also just one group element, if I'm not blanking. You could use a different polynomial commitment scheme, and if the polynomial commitment scheme doesn't require a trusted setup, Marlin wouldn't either. But all other polynomial commitment schemes have bigger proofs, bigger evaluation proofs than KZG. So you'd kind of be giving up one of the nicest properties of Marlin. And universal here just means that one setup works for any circuit up to a given size bound. In contrast, another popular snark, which has even better verification costs, namely Growth 16, has a circuit-dependent trusted setup. So if you change like the circuit you're interested in proving a statement about, you have to rerun the entire setup ceremony. Okay, so that was Marlin. Today I want to start talking about front ends. So these are procedures for kind of taking like statements that the prover wants to prove and turning them into equivalent instances of like circuit satisfiability or rank one constraint satisfaction, or Ayer or Planckish, whatever kind of circuit people like to use today, so that you can then apply a snark like Marlin to that circuit. And if we have time, I'll begin talking about lookup arguments, which I kind of think of them as kind of living in between front ends and back ends. And I'll explain what I mean by that if we have time to start on lookup arguments, and if we don't, I'll explain what I mean by that next meeting. Okay. Does anyone want to ask a question right now? Okay. Someone want to confirm you can hear me? See my screen?
Mm-hmm. Yep.
Cool. Okay. Thank you. So with snarks, I'd say like the ideal scenario, which is still a little bit aspirational today, is that a programmer writes like a computer program. Ideally in like a high level language that we're all familiar with, like Rust or Python. But today people actually have to write these programs in domain-specific languages that engineers are very carefully developing, whether it be Circom or Bellperson or Cairo or what have you. There's a lot more, Nor, Leo. So anyway, you write a computer program that takes as input the witness that the prover is claiming to know. Let me call that witness W, and checks that W satisfies the property that the prover claims it should satisfy. And let me just call that the property of interest. So if you want to make this a little more concrete, let's say the prover is claiming to know, a pre-image of a certain output of a hash function like SHA. So in that case, the computer program would take as input the purported pre-image. It would evaluate SHA on that pre-image and check that the resulting output equals whatever the prover says it should equal. Right, and as we we've now seen a bunch of snarks. We for example we saw Spartan and Marlin, and these were snarks. I presented them as snarks for rank 1 constraint satisfaction problems, which is a generalization of arithmetic circuit sat. And so we sort of have a disconnect here because our snarks allow the prover to prove, given an agreed upon circuit, that it knows the satisfying assignment to the circuit. Okay, but this computer program is not a circuit, it's a computer program. So we kind of have to turn the computer program into an equivalent circuit, meaning the circuit has a satisfying assignment, or sort of, I don't want to say this. Well, I'll make precise exactly what we need in a moment, but basically satisfied the circuit, we want to be equivalent to, knowing a satisfying assignment to the circuit is equivalent to knowing a W that the computer program would output 1 on, with 1 indicating acceptance that the W satisfies the property of interest. So that's the gap that front ends bridge. And I guess one way you can view it is like circuits are some kind of very low level computational model. They're sort of like a computer chip, but where the only primitive instructions are addition and multiplication over whatever finite field the circuit is defined over. And moreover, like data flow and memory is very limited. So circuits, we should, since we've been studying snarks for circuit sat for a while, this shouldn't be new. But just as a quick reminder, a circuit takes a bunch of field elements as input. So say the input is 2, 3, 1, 6, and gates either will multiply or add together 2 different input values, producing ultimately 1 or more outputs. So this is an example of a circuit. And yeah, so the only primitive operations allowed are addition and multiplication over the field, and data flows through the circuit via these wires, with each wire connecting 1 gate to another gate, and every gate typically being required to have fan in at most 2. R1CS kind of generalizes the fan-in of addition gates to be unbounded, but the multiplication gates definitely need to still have fan-in at most 2, even in R1CS. So it's these wires connecting 1 gate to another gate is kind of a very limited form of data flow. So it's programming a circuit is is kind of difficult. It's not like writing a Rust program where the language is just much higher level. The primitive lots of things are primitive operations. If you run the Rust program on your laptop chip probably has 1,000 primitive operations built in, and they're far more complicated than just addition multiplication. And your laptop has random access memory rather than connecting 2 different gates by wires or something like that. And so kind of the low level nature of the circuit computational model somehow lets us design snarks for it. The machinery underlying snarks is sort of low degree polynomials. So any individual gate in a circuit is kind of, intrinsically a low degree polynomial, like addition gate is degree 0, and a multiplication gate, or it's degree 1, sorry, and a multiplication gate, Fandon 2 is degree 2. So each individual operation in the circuit is like low degree, and that kind of plays nicely with the low degree polynomial machinery. That's why we have snarks for such a low level computational model. And yet what programmers want to program in is not, they don't want to like write the circuit I just drew in this picture themselves. They'd rather write a program in a high level language and then just have a compiler that does the transformation from the computer program to the low level thing, like the same way, the compiler you use to run a Rust program, automatically turns your high level computer program into machine code that your laptop can run. Okay, so the goal here is to take the computer program, I guess let me call it psi, and turn it into a circuit C, and let's say C. How do I want to put this? Let's say C takes 2 inputs. Let's say 3 inputs. Though I'm going to want to drop this notation shortly, but 3 inputs. Let's say, I'll just do 2 inputs just to keep it simple. W and W prime, such that, I'll put it this way: like phi of W equals 1, if and only if there exists a W prime, such that C of W prime equals 1, and moreover, W prime can be computed quickly given W. And what's happening here, the way to interpret this is, so W here is the part of the circuit that is like the in the zero knowledge setting, you would consider it the prover's like private input. So it's the witness that the prover is claiming to know, and using the snark to convince the verifier it knows this W that such that via W outputs 1 when run on W. And W prime is what's called advice inputs, and they're kind of there. You think of them as like untrusted advice that the untrusted prover provides to help keep the circuit small. And, the example I always bring up to try to illustrate this is, if the computer program phi, like during its execution, like takes a value y and inverts it, turns it into y inverse, then, computing y inverse from scratch is very complicated, especially if you only have access to addition and multiplication operations. But the circuit can take as an advice input a value that should be set to y inverse, and then the circuit can just multiply the two together, y and y inverse, and confirm that the output is 1. So like the verifier needs to insist that this gate outputs 1. So you think of the circuit sat instance as taking y inverse as untrusted advice and doing a short little check to confirm that y inverse was indeed provided correctly. It's untrusted advice that has now been checked, and that's much simpler than computing y inverse from scratch. But when we ultimately apply a snark for circuit sat, the prover is going to have to cryptographically commit to sorry, I'm in New York City now and it's very loud outside, so I might just get a little distracted at times, but the noise is going away. It's the prover does have to cryptographically commit, like in Marlin or Spartan, to the value of every gate in the circuit. So it's not like the untrusted advice inputs are coming for free. like the prover is going to have to cryptographically commit to each untrusted advice input, but it's better to commit to like one untrusted advice input and have a single gate like check its validity than it is to compute the value from scratch, which would require the prover to commit to the values of many gates rather than just, I guess, two here, one for Y inverse and one for the multiplication gate. Actually, the prover wouldn't even have to commit to this multiplication gate necessarily, because it's sort of implicitly claiming that the value is 1, so it doesn't have to explicitly commit to that value. In fact, it's just sort of implicit that, the value should be 1, otherwise the verifier will reject. Okay, so that's what a front end should do. It should turn the computer program psi into this equivalent instance of circuit sat. So basically, the prover knowing a satisfying assignment W to psi is equivalent to the prover knowing a satisfying assignment to the circuit. Okay, any questions? All right. So if you've never like worked with circuits before, they take a little bit of getting used to. Like it's just like a weird, computational model, and like you can program it like any other model, but like kind of the lower level the computational model you're programming, the more it takes, getting used to. I think it's like, would be really strange for us to write like assembly code today, and but if you do it a bunch, you just kind of get used to it, and you've learned the tricks and stuff. And so it's similar with circuits. I want to start today by discussing circuits without any advice inputs. Kind of just to get used to programming circuits before we deal with the whole, I think of, allowing the circuit to have advice inputs. I think of it as like non-deterministic programming, kind of, where you're allowing this untrusted prover to kind of help out your program to keep it fast and the circuit small. But you always have to like check the validity of the untrusted advice. So that's kind of just an extra wrinkle beyond programming circuits when you don't have advice inputs. So let me just start with a quick example that I like, which is naive matrix multiplication. So like written in a high level language, like the input would be two matrices like A and B. Let's say they're n by n matrices with entries from our field. And the goal is to, multiply the two matrices. And here's, the standard algorithm for it. It's not the fastest known algorithm, but it is sort of the simplest. So it's just a triply nested loop. So for I equals 1 to n, for j equals 1 to n, for k equals 1 to n. I guess I should have initialized my output matrix to 0. So we set Cij to whatever, plus equals Aik times Bkj. I think that's the right definition, the right algorithm for naive matrix multiplication. And then at the end, we just output C. Okay, so that is a triply nested for loop. And here, what's really nice about this program is it basically is an arithmetic circuit. So the only operations happening are addition and multiplication. So this turns like directly into a circuit, and I'm going to like draw the circuit in a moment. Basically like arithmetic circuits they basically are like straight line computer programs that whose only operations are addition and multiplication. I guess by straight line, what I mean is like no conditional statements, no, if, then, else, and just straight up like, maybe you do some loops with some predetermined iteration number. And then in each iteration, you just add and multiply things. And that's basically a circuit. So let me just do a little example. I'll just do 2 by 2 matrix multiplication. So let me say A is, and I'm going to write A out as like a vector, but think of it as, like actually two rows. So I don't know, 1, 3, that's the first row, 2, 4, and then let me say B is 0 to 1, 6. Like, it doesn't really matter. And yeah, so there's going to be n cubed multiplication gates. So this is like A11. So like A12. This is A21. This is A22. Let me just do this. All right. So yeah, we need to multiply. So we start with C11. So that is gonna go over row 1 of A and column 1 of B. So here's row 1 of A, and I guess these are the 2 entries of column 1 of B. So yeah, so there's going to be a multiplication gate. Going to multiply A11 and B11. And there's going to be a multiplication gate that multiplies, A12 and B21. Right, and they get added together. So this addition gate is one of the outputs. So this here is C11. That's the output. Maybe I won't do the whole thing because it'll just take me forever since I should have done this out in advance. But let's see let's at least do C12. So that would be going again over row 1 of A. So there'd be a multiplication gate with multiplying A11 and B2 B12. Yeah. Correct me if I'm making a mistake. It's been a long day, and I very likely cannot implement naive matrix multiplication correctly on the fly. So just let me know if I screw it up. And then A12 times B22, I think. And then you add those two up, and you get that would be C12. Okay, and so there'll be 2 more output gates. Computing C21 and C22. And each of them would involve 2 more multiplication gates and 1 addition gate, for each. So that's what the circuit would look like. So I always think that this is a good example to have in mind, both because the high-level computer program kind of directly turns into a circuit, but also because it helps to it helps as a reminder that the front-end techniques people use today, in particular, a very, very popular technique is colloquially called ZKVMs. Okay, and these are techniques that sort of front ends sort of implementing a CPU or virtual machine abstraction. These are just synonyms. And basically, what this means is you sort of imagine your computer program is written as kind of assembly code for a certain CPU, whether that CPU is like the Ethereum virtual machine, or the CPU is the Cairo CPU, which is, a CPU that was kind of hand designed for snark friendliness in a sense, or whether it's the RISC-V instruction set, which comes from the computer architecture community. And these ZKVMs, like the front end, will actually kind of produce a circuit that kind of runs or implements the program, or runs the CPU for a certain number of steps. So like the prover saying, hey, I ran like this particular like RISC-V program. So this particular program written in RISC-V assembly for 1 million steps. And the produced output was blah. And so the circuit then that the ZKVM front end will produce kind of actually implements like 1 million steps of the particular virtual machine. Again, CPU and virtual machine in Snark world are just synonyms. I think they have slightly different meanings in like actual, computer systems, I believe. Don't ask me to clarify the differences. But in Snark design, people use virtual machines and CPUs as synonyms. And so like at each step, so basically at each step, like the circuit implementing like the CPU, will kind of figure out like what instruction should be executed at that step, right? And like the RISC-V instruction set, there's like 60 different primitive instructions. Cairo only has like a handful of primitive instructions. EVM has like 100 or something. And so it'll figure out which instruction should be executed next and then execute that instruction. Okay. So it's literally like it's literally like the circuit itself is like running the CPU, running the virtual machine for a fixed number of steps. And one thing I like to sort of point out from the start, given how popular ZKVMs are, is that this generally confers, at least today, enormous overhead, right? So like you could never get, here is a circuit of size n cubed, maybe, literally each step of this computer program turns into like one gate of the circuit. So each multiplication turns into one multiplication gate. Each addition turns into one addition gate. So there's like really no overhead at all from the front end here in turning this computer program into this circuit. And that's without even including any advice inputs at all. Okay. If we were using a ZKVM, right, then like kind of at each step of the computer program, like the circuit implementing the virtual machine will kind of have to be prepared to execute like any possible instruction that might get executed at that step. And so it's kind of over prepared and paying an enormous price. Sort of has to figure out from scratch in each step that, hey, like now it's time to multiply AIK and BKJ, so it's just like a multiplication instruction, or like, hey, now it's time to add, the result of some multiplication to CIJ. Whereas if you know in advance that like, all your computer program does is addition and multiplications, you don't actually need the circuit to include any logic to figure out, at each step, like which instruction is going to be executed. You just kind of have the circuit directly, do that, the relevant instruction. So yeah, like if you take the ZKVM approach and you apply it to this computer program, you'll get like a much bigger circuit than this one right here that kind of just directly implements the computer program, because the computer program itself is just like a straight line program that only does addition and multiplication operations.
Yeah, I got a question.
Yeah, please.
So the overhead comes from like, say, like a push or like a memory, as opposed to just as we did in the first example, which is taking the loops and doing them directly into the circuit. How do we translate between, again, like a CPU action into the equivalent circuit?
Like so I'm going to try to get there today. It's a little when you first see it, I haven't found like the best way to explain it, but like that's kind of the goal of getting through in this session. I mean the circuit like really will work as I've indicated here. Like literally like the circuit just 1 million times it will figure out what instruction to execute and execute it. Kind of the same way the computer program itself does. But what I'm hiding here is like kind of how do you figure out what instruction to execute and how do you execute that instruction kind of in a circuit when your primitive operations are just addition and multiplication.
Yeah, I can see how that can be tough. I guess that's assuming we're going to like only an R1CS and not a more complicated arithmetization.
Yeah, I mean, I wouldn't say it's really conceptually any different whether you're using AIR or Plonkish or R1CS or arithmetic circuits. Um, where these things can differ is just in terms of like the concrete size of the resulting circuit. But as far as like kind of what the circuit's doing, it's all the same. It's just the more expressive the kind of circuit, the smaller it can be. If you're allowed to do like more than just additions and multiplications, then you can implement some instructions with fewer gates than if you can only do additions and multiplications or something like that. But conceptually, the fact that you can turn any computer program into a circuit should be like just clear, because ultimately like your laptop is a circuit. Now it's not as simple as just additions and multiplications, because modern computer chips have like, I don't even know, 1,000 built-in instructions that it kind of just does each in like one step, whatever that means. So it's a way more complicated kind of circuit, but like ultimately it's just it's got these gates. I don't know anything about hardware, but it's like voltages are shifting, and that's going to tell you whether the gate is evaluating to 0 or 1 or something. And so this is just some like especially simple, these arithmetic circuits are just like especially simplified versions of what your laptops are actually doing right now as we're talking. But of course, that's not very conceptually helpful to understand, like, conceptually what each part of the circuit is like actually, implementing or whatever.
Got it. Yep. Thank you.
Okay, other questions? Cool. Yeah, questions are going to be great today. Like this front end stuff is like, I don't think there's like really a way to express it like super precisely without obviously if you actually just like look at the code of a front end, like that is essentially a formal specification of the front end. But like I haven't really found a way to not be pretty hand wavy in describing the concepts. So questions are going to be really helpful, especially today. Okay. So I guess I want to now I want to explain. I think I've already, hopefully it's already made clear why advice inputs are powerful, like just from the example of like division or inversion of a field element, where it's much simpler to have the prover provide like y inverse, and the circuit can just kind of check that y inverse was correctly provided by multiplying y and y inverse and making sure the output is 1, than it is to compute y inverse from scratch. But there's kind of a much more general statement I can make that sort of indicates why advice inputs are powerful, or more precisely, why the lack of advice inputs, if you don't allow any advice inputs, it's bad in general. And that is the following. So it's known that you can take any computer program running in time t, and of course, to actually be precise, you'd have to, the computer program, is you'd have to tell me like what CPU, what virtual machine you're actually programming, but let's not worry too much about that right now. So running in time t, and turn it into an equivalent circuit of size about t squared. So it's really like, I don't know, t squared log t or something. And a little more precisely, it's if the circuit, if the program uses space s, like s bits of space, the runtime of the computer, the circuit size is about t times s. So I think it's like t times s times log t, or maybe I'm missing like another log factor or something like that. Okay, and this is what I mean here is if the computer program, so there's no advice inputs here. So that is for any x, phi of x equals c of x. So we're turning. There's no witnesses or whatever. Like both the prover and verifier know x. If you're going to apply any kind of snark to this circuit, this is like a public input. Everyone knows it. And the goal is just to evaluate, to run the computer program on X and figure out what the output is. And so running the computer program on X is equivalent to like applying the circuit to X. So this is a transformation from the computer program to circuit evaluation, not circuit satisfiability. Right. Again, the difference is basically the input to the circuit is fixed, and there are no advice inputs, or should I say, if there is an advice input, the prover can't just succinctly commit to it. It's going to have to, like, if you were apply a well, let me just there are no advice inputs to the circuit. All right, and the reason this is bad is because of this S factor here, right? So like if you have a computer program that runs for 1 million steps and uses space close to close to 1 million bits of space, the circuit size will be like over 1 million squared, which quadratic blow up compared to the runtime of the computer program, and that's like completely untenable. And so with advice inputs, we can get rid of this factor S completely. So let me just sketch how this works, with the S and, without using advice inputs. And then I'll try to explain how it works without, with using advice inputs to get rid of the S. Okay, any questions about this statement? Okay, so basically, like, since the computer program uses S bits of space, that means if I tell you all the contents of the computer program's memory at any given time, the state of the program, right? Like all of the data that the program has is stored in memory, right? So and then to advance the program one step, the program, at each step of the CPU, what happens is some instruction gets executed, and these primitive instructions for any CPU, they do reads at most one memory cell. So it does at any step of your computer program, the computer program, it's not allowed to scan all of memory in one step, right? Every time it reads another memory cell, that's another step, right? So at each step, it can only read one memory cell, execute some kind of simple instruction that alters or writes to at most, let's say, one memory cell, and then maybe not one, maybe it alters 3 memory cells or something, but it's not going to suddenly change all of memory, to write to a huge number of memory cells. You have to, it costs more than one instruction to do that. So what the circuit's going to do, and as you're seeing, I'm being pretty hand wavy, right? But hopefully the main ideas are going to come across. The circuit is just going to kind of run the computer program for, all T steps. T is the runtime of the computer program. And at each step, it's going to have a gate devoted to each bit of memory. So conceptually, we're going to have, S gates, storing the initial contents of memory, when the computer program starts. And what you'll do is, let me actually get this out of the way. Yeah. And, so part of memory is going to be the public input to the circuit, and the rest is just in I guess let's call it all zero. Like let's say memory. Every bit of memory is initialized to 0, something like that. And the computer program, like you execute the first step of the computer program, right? And that's going to like read at most one memory cell. Let's say it reads this cell, and like based on what it reads, it does some simple other stuff, and so only only a handful of things of memory cells get their values updated. I don't know, let's say like this one and this one get updated, and so there's just like going to be some simple logic. I know this is super hand wavy, but let me just say simple logic implementing one step, like the first step of the computer program. And what will sort of come out of the result of that simple logic is going to be the entire contents of memory after step 1. Okay. Yeah. So this is sort of the where I wave my hands like all day through this session. Simple logic implementing one step of a computer program is like a very vague statement, but like essentially computer instruction set architectures are defined so that each individual instruction is like very simple, and so you can kind of turn it into a circuit, and the circuit won't be that big. And so that's like this simple logic implementing one step. For now, you can just think of it as like we take, I don't know, each of the 140 EVM instructions, and we just hand code a gadget that implements the instruction, and this simple logic just checks which instruction should be executed. And because it's a circuit, if you're very naive about things, you maybe have to actually have gates implementing every possible one of the 140 instructions at each step, which is of course completely impractical. And in general, we have ways to avoid that. But then you can just have some kind of switching circuitry that says, hey, if at this step I should execute this opcode, well, let me just kind of only turn on like that particular opcodes like gadgetry, and the other ones will just kind of be fed garbage inputs that cause it to just be ignored or something. No, I'm being super hand wavy here. The point is what comes out is just the contents of memory after step 1, and so you just keep repeating this, and the computer program, we're assuming like we know it runs for at most t steps. Okay, so when you finally get to like the tth step, you've computed the entire contents of memory after step t, and that that has in any computer program, after it terminates, there's some memory cell storing, like say you just define the computer program, so like the output is in the if there's only one output, just have the computer program store the output in like the first memory cell, so like in the first gate or gates, and at the final layer of the circuit. And so yeah, again, like up to my horrible job of explaining what I mean by simple logic implementing one step of the computer program, you see what's happening is the kind of the goal of the circuit is for each of the t steps of the computer program to compute like the entire contents of memory at that point in the program's execution. Okay, and the important point here, the reason this is awful, okay, is because for each of the t steps of the computer program, we have s many gates. I mean, there are other reasons it's awful too, like the way I sketched how you would implement, one step of the computer program. What I sketched was also awful, because you're kind of what I sketched was you're kind of paying in the circuit, trying to execute every possible instruction at every step, when in fact only one instruction gets executed at each step. So that's also terrible, right? It's like awful if you have 140 instructions to kind of pay a cost as if you literally executed all 140 instructions at each step when only one of them mattered, only one of them actually got executed. So that's another issue. There's lots and lots of issues with how I sketch this, but the most fundamental one is you really don't want to pay, S many gates at each step of the computer program if S is large. Okay, and so most, remember, at each step of the computer program only changes like a handful of memory cells, and so like most of these gates being having S gates for each step, like most of that is wasteful. Like most of the circuit just winds up like copying memory cells like from one step to the next. Conceptually that's the net effect, right? Because at each step the computer program only changes a handful of memory cells, and yet we have logic that's kind of for each and every memory cell at each and every step, figuring out what its value is. So somehow, like, in a priori, before you run the computer program, you don't know like which are the handful of cells that are going to get changed at each step. So we have to have circuitry here to kind of for each memory cell figure out like what is its new value. Did it get changed or not? But like post hoc, after the program's been run, we've actually only done like a constant amount of work. We've only changed a constant number of memory cells at each step. So like most of this stuff was just wasted, was just wound up copying one memory cell, unchanged from one step to the next to the next. So that's kind of the waste that advice inputs managed to let you avoid. Okay, questions at this point? That was super hand wavy. You sure no one wants to ask a question?
Yeah. Well, I have a question.
Yeah.
In this depiction, we're talking about a VM here.
Mm-hmm.
And I'm relatively early in my understanding of how to like code these circuits, quote unquote, by hand. Because I've seen like in Halo 2,
Mm-hmm.
you could set up your whole trace table and then just like pick how each cell relates to each other. So I think that also uses advice. So I think there's two different things here. We're talking about VMs, and then there's this raw circuit approach. Am I thinking about this correctly?
Yeah, I think you totally are, and that's sort of what I was, the sort of thing I was getting at when I, introduced the matrix multiplication circuit and the ZKVM notion. Try to explain that the ZKVM notion, like in general, supporting a virtual machine abstraction might be introducing a lot of overhead. So with Halo 2, you're right. You sort of directly program, like writing the circuit in Halo 2. It's as if you're saying, well, here's a multiplication gate that connects, this input and this input, and then here's another multiplication gate whose in neighbors are this input and this input, and then here's an addition gate whose in neighbors are this multiplication gate and this multiplication gate. So I think with Halo 2, I haven't programmed it in myself, but I think like it's actually right now it's not combined with the front end. It really just is like you let the developer write the circuit, and Halo 2 is a back end, will then like apply a back end, which is basically like Plonk, but with, you get to pick like bulletproofs or KZG as the polynomial commitment to that circuit. When you are a developer who's kind of, programming the circuit gate by gate, and, of course, Halo 2 supports Plonkish circuits, so, it's not literally just addition multiplication, so they'll call them constraints and stuff rather than gates. So you have very fine-grained control over what the circuit's doing, and so you can do a lot of, like, clever, things to make the constraints, really, compact. So there's, minimize that, like basically avoid all the overheads that you might have if you instead take the ZKVM approach. And the trade-off in general might be kind of performance, basically how big is the circuit that you wind up applying the backend to versus usability. Because, it's you need kind of like an expert to, program a circuit gate by gate because it's such a low-level computational model. Like in the same way, like trying to get someone to program an assembly today would be like impossible because no one knows how to do that anymore since they all just like write in Rust or whatever, since it's much easier to program in the higher level language. Whereas ZKVMs, will let somebody program in some higher level DSL. The aspiration is to let people program in whatever language they want, like Rust or something. And I guess like the RISC-0 is sort of targeting that. The idea is there are all these compilers that will take computer programs like Rust and turn them into RISC-V programs and then they in turn have a front end that turns a RISC-V program into an AIR, and then they apply like a Stark backend to the AIR, right? So there's a trade-off between like performance and usability. A lot of people think like the performance is already good enough that it makes sense to have the usability. I don't think that's true today, personally. I guess if it were true, certainly it's like application dependent, right? If it were true, like why would anyone be writing their own constraints in Halo 2, right? They would like write in Rust, right? And like save themselves like many, many hours of effort and many, many possible security vulnerabilities because, it's much more error prone to program a constraint system by hand than it is to write a Rust program, I think. There's a kind of just performance and auditability trade-offs versus usability is my view. Is that helpful? Did that make sense?
Yeah, and which one would be more usable, I guess, as you were describing the higher level language compiling down to the that's compatible with like the RISC-V is
I think the thing that will be most usable is if people can write in Python or Rust or something they're comfortable writing in, and they don't have to know anything about snarks, right? They write this program that takes as a witness, and we're not there today, and I think it's a mix of just the tooling needs to get better developed, and it's not that there's necessarily like a technical barrier. It's just it takes a lot of engineering and effort to develop the tooling that allows for that. And then I also think it's a performance issue where if we actually implemented that today, I don't think I basically think the circuits will be too big, that the prover, when you apply the backend to it, will take too long. And we'll see, because the RISC-0, I believe, is like aiming for this aspirational thing where people will write in whatever language they want, and existing compilers will turn it into RISC-V, and they'll turn the RISC-V into an AIR, and they'll feed the AIR into a Stark. So we'll see what the performance is. I think for some things it'll be okay, and for others I think it will not be even close to okay. So it all depends.
Yeah, I have one additional, but I can save it to the end. I don't want to.
I think this stuff is good, and it breaks up my horrible hand-wavy struggling, which is what I always hit with front end. So I think you should go ahead.
Yeah, well, the VM explanation was super helpful. I guess what I'm also trying to think about is if you were to use a DSL, can the output just be like an execution trace for, say, in like a Plonkish or R1CS, that you can then literally just take and plug into whatever backend you want, much like you just described? Because I'm trying to use, for example, like Jellyfish or like the Plonky 2, which has just add and mult, and I'm just fervently trying to avoid doing the almost naive approach, which is program these circuits directly. So I'm trying to, again, maybe use like a Noir to compile down to a Plonkish and then just grab that. I'm just trying to figure out like what the dev pipeline would be outside of VMs on just like a circuit level. But we can answer this at any time. Just more of a personal question.
Yeah, no, I mean, it's a great question. I don't know all of the ins and outs of all of the available tooling today.
Yeah.
So your question sort of hits both like, what is available today and like what's possible in principle. So a few months ago, people I think would have said, well, not all snarks can, prove statements about plonkish or error. So you couldn't just sort of plug in any backend. You need one that can, ingest, prove statements about, your particular circuit, that, kind of circuit that your DSL sort of the front end compiles, programs in the DSL down to. But I think, I've been shilling to you all this paper on, CCS, customizable constraint systems, which kind of points out that at least the Spartan and Marlin, which were originally described for R1CS, actually can prove statements about any of the circuits people are using today. So I mean, basically, I think what the vision you would like, which I think is actually the ideal. I think is largely doable. Most snarks can prove statements about most kinds of circuits that people have started using today. So it should be possible to write in whatever language you want, whether it's a DSL from a ZK company or just Rust or something. Apply a front end that turns it into, pick your favorite kind of circuit, and then apply like any back end, because almost any back end can prove statements about almost any kind of circuit anyone's been cooking up today.
Yep.
The tooling today definitely does not support something like that. I mean, Spartan and Marlin, today are only implemented for R1CS, even though they can be tweaked to handle the other kinds of circuits too. I don't know. I'm going to say this. I'm not really aware of a front end, like an automated compiler from a higher level DSL that spits out plonkish. And I think, my impression is, the Zcash folks who started Halo 2 are kind of all about programming these constraints by hand for performance reasons.
Yeah.
And so, have no interest in there being a front end there. And, now Halo 2 is a broader community project. And so I think eventually I'm guessing there probably will be some front ends integrated with it, but I'm not aware of that having happened today. And, with the various DSLs Noir and Cairo and what have you, I don't necessarily know what backends have been integrated with them. So obviously Cairo is only integrated with Starks because it's from, Starkware. With Noir, I don't know the details, so I could find out and get back to you. I mean, I know, Aztec is all about plonkish as well. So,
yeah, they shipped. Yeah, they shipped Bartenberg. I think I'm saying that correctly, as the back end. And then, because I pinged them on Discord and I said, hey, how do I work this with Plonky 2? And they said you have to write an adapter. And frankly, for me, that was a little lost in what that meant. So my assumption was, hey, if I can just grab whatever Noir outputs because it's compatible with a Plonkish scheme, and then just literally plug that into Plonky 2, maybe that's the adapter they're talking about, and there's no other sort of circuit translation required. But that might be too easy of a translation, if that makes sense.
Yeah, I think, I'm going to say something, embarrass myself getting details of the current projects wrong, but I think Plonky 2 is air based, and air is a special case of plonkish. It's kind of a highly uniform variant of plonkish. Right. So, then does anyone else on the call know, can correct me? Obviously, Plonky 2 is sort of suggestive that it would support plonkish, but I actually think what it refers to is kind of taking the ideas of the Plonk proof system, applying them to air, and switching the polynomial commitment to Fry.
Yeah.
I think you're correct. I think they have Starkey, which is kind of the back end, and it gets pushed to the smaller snark with Plunky. So it's two different things, but I think you're right.
Yeah. Okay. So, if I'm right that Plonky 2 or Starkey or one of the two, if anything that only ingests air, is not going to you're not going to be able to automatically feed it a plonkish instance, because air is a special case of plonkish.
Yeah. Right. Okay.
So yeah, that would be a technical bottleneck there. Yeah. By the way, Aztec is. I think this is public, so well, they're ultimately going to switch to something kind of related to hyperplonk, which will still be targeting plonkish, but the back end will change. Like you remember, I said like Spartan can prove things about any kind of circuit people are using today, and hyperplonk was sort of a similar thing, but for plonkish. So they're switching to something in that direction. And so that is, this isn't helpful today, but it's pushing, towards the notion that you should be able to, apply any back end for kind of any kind of circuit. Yeah, but the tooling just isn't there today. It's a really big project to switch the back end, especially. Yeah. Anyway. Okay, so yeah, that probably wasn't too helpful, but I think it's good context, good discussion for just discussing this current situation.
Yeah, you have to commit to an entire stack almost at this point.
Yeah, I hope it changes soon. I have something coming out on new lookup arguments, which I think will help at least the performance of the ZKVM approach, and also I think it'll just simplify a lot of stuff. I think it'll make the circuits much simpler, make it just a little easier to swap things in and out. And so I'm actually hoping the timing works out that we're kind of still talking about front ends and lookup arguments when I'm ready to talk about this work, and then we can discuss that here. And yeah, I mean, we'll have to see, but I think it might make the current situation a little bit better. Again, there are two issues today. It's just the tooling is, it just takes so much manpower to develop. It's just not where it could be given current technology. But then there's just the performance issues of the current technology. Yeah, I do hope it'll get better soon.
I had a question about that. Like your explanation a little bit further down sounds very much like folding schemes. Like the difference between Nova and Supernova. Like you get a la carte. I'm just wondering, if you have better lookup arguments, people still need to use Nova or folding?
Yeah. Okay. Yeah. Great question. So, okay. Let me maybe take a quick step back and just give some context with, just for everyone else, I guess. So Nova folding scheme, it's a snark for iterative computation. So applying some simple function f over and over again. And this looks a lot like a CPU, right? Because the CPU, I was saying, it's got this very simple instruction set, and at each step it applies one instruction. So each step is very simple, but you would do it over and over and over and over again. And after a million steps, you've actually run this very complicated program. And indeed, you can actually express any computer program in this way. And the only headache, and actually there's probably another paper to be written about this, is sort of exactly the issue that came up in this circuit, which is kind of propagating memory from one step to the next, right? Because the transition function of a modern CPU, each step might involve a read in the memory, but modern computers have random access memory, so it could read any cell of memory. And so, from step to step to step of the CPU, you do have to sort of propagate the full contents of memory. But then, each step of the CPU only reads one of those one cell of memory or something, and does something very similar based on it, and changes one more cell of memory, and then you're done that step, and you go on to the next one. And there are ways to deal with that. I think the way people would deal with it today is basically with Merkle trees. So each read, basically you'd feed into this F that captures one step of the CPU. You need F to sort of take in a Merkle authentication path associated with every read, and check check that the path is valid, and at all times you have a special register that's storing the Merkle root, which lets you sort of kind of make sure that each authentication path is really valid for the current state of memory. So basically, up to the details of how you kind of propagate memory from one step to the next, CPU execution is exactly this iterative computation. that a folding scheme like Nova is tailored for. And that Merkle thing to deal with memory is expensive, and I think there are significantly better ways to deal with that. And they haven't been written down in the literature, but so let's just I guess move on and ignore the issue. So the big benefit of Nova over what people are using today for like ZKVMs, well, it's really the starkest one, like no pun intended, is prover space. Because if you take what I call a monolithic snark, basically not a folding scheme, and you apply it to a circuit, right? The very first thing the prover is going to do is like commit to the value of every single gate of that circuit, right? And that's going to be like the prover, especially if you're using like Fry, right? The prover is going to take that entire vector of gate values, right? It's going to apply a blow up factor to it. So basically treat it as a univariate polynomial and evaluate it at 4 times as many points as like the number of gates in the circuit, thereby quadrupling the prover space. And moreover, like there's to do that, there's an FFT, which itself is like really space intensive typically. And then like Merkle hash all the results. Whereas with Nova, it's sort of the prover can like run each step of the CPU in its head. Apply each F here is a step, implementing one step of the CPU, and so the prover doesn't have to have in its head the value of every gate in the whole circuit, computing many copies of F, right? It can kind of focus on like a single copy of F at a time, whatever the current step of the computer program is. And so the prover in its head can just maintain like the computer program's memory as it's running the computer program. And really that's it. Like it doesn't have to deal with like an execution trace of the whole computer program. It can kind of just focus on like just the current state of the computer program right now as it's running the program in its head. And there's some other like time benefits as well, but that's really like the starkest benefit over all the other approaches that people are using today. Okay, so back to the lookup arguments. So this work I have in progress, I mean, I'll tell you, like it's the way it turns every step of the computer program, just into a lookup. So the idea is, at each step of the computer program figures out what primitive instruction should be executed at this step, and then it executes the instruction. And we're going to have like a lookup table, which is literally like the evaluation table of every instruction at every possible input, right? So like, if there are 100 instructions and each takes two 64-bit inputs and produces some output, right? Then this table is going to have size like 100 times 2 to the 128, right? Because there are 2 to the 128 possible inputs to each of the 100 instructions. And, it sounds crazy, like that table is way too big for anyone to materialize. But these instructions, because they're primitive instructions, they're like very simple. So this giant table is like very structured. So no one actually, neither the prover or the verifier, needs to materialize the whole table. They kind of like only pay for the entries of the table that are actually looked up, right? And like obviously those entries that are actually looked up are like very efficiently materializable because each one is obtained by just executing a primitive instruction. Right, like you want to know what's the XY entry of this table, the evaluation table of some instruction. Well, just evaluate the instruction on XY, and you'll know what the entry is, right? So, all of that, so that will help make the circuits much smaller, because rather than having like gadgets implementing each of the 100 instructions in 140 instructions in the EVM or something, we'll just have a lookup table, for each of them. But that doesn't. I still would like to use like a folding scheme like Nova as the back end, because there'll still be benefits to that. So like basically you can think of this as turning the one step of the CPU, turning it so that function, let me call it F. This lookup argument will let you turn F into a much smaller circuit that really just does a lookup, and that's kind of it. But there's still sort of downsides to having to deal with all applications of F at once, rather than what folding schemes give you, which is sort of, the prover being able to run the CPU one step at a time and only have to focus on that step at that time, rather than having in memory, like, the entire execution trace of the whole computer program all at once. Was that helpful? I know that was rambling roundabout. Did that clarify things at all?
Yeah. I think we're on the verge of really good front ends, and it sounds awesome.
Yeah. So we'll see. There's still definite overheads to having the virtual machine abstraction, but yeah, I think it is much more kind of developer friendly. So if we can bring the overheads down enough, I think that'll be that'll be interesting. Cool. All right, so we're already an hour 15 minutes in. Let me see. Do I want to try to explain? Maybe so let me explain front ends that will turn like witness checking programs into circuit satisfiability instances using a lot of advice inputs. And I'll try to keep this to 15 minutes. And it's going to be super hand wavy no matter how long I spend on it. So it's probably better to keep it short. And we can, we're going to keep talking about this stuff next session. So I think it's fine to have more content bleed into the next session. So yeah, here's roughly how front ends work today. And again, this is going to use like a lot of advice inputs. So so the prover, claims it ran some computer program psi on a witness W. And so this is what it's going to do. We're going to have a circuit sat instance that takes as input not just W, but the entire, let me call it the execution trace of psi when run on W. Okay. And you should think of this as like the order like T times S, like the values anyway, of the circuit, that didn't have advice inputs before, like, but with all the redundancy removed. Okay, let me, that probably didn't make any sense, so let me try to explain what I mean by that. So remember, like, the gross overhead before was, like, at each step of the computer program only changed the value of, like, a handful of memory cells, and yet we had, we paid for, like, gates and circuitry for each and every memory cell at each and every step to see, for each memory cell, we were like, hey, was this memory cell changed at this step? No. Well, then, just set it to the same value as before. And only for a couple of them was the answer yes, in which case they wound up, the circuitry updates the value. So all of that just copying almost all the values of memory cells from one step to the next, that's just like waste, right? So this circuit transcript is like basically the values of all these gates in the circuit with no advice inputs, but just with all the redundancy removed. So what I mean is, like, for each step of the computation, we're just going to list like what memory cell was read. I don't know what instruction was executed. I think that's typically most computer programs. This is way too low level for me. So, but just store like the next instruction that should be executed, like in something called the program counter, I think. Whatever. Like I said, I want to be hand wavy, and I probably can't not be hand wavy. Like the output of the instruction, and like that output typically gets like written to some memory cell. So like you would want to also specify the memory cell that output was written to. So that's kind of like this information, and again, obviously being super hand wavy, very informal. But if I tell you this information for every step of the computer program, I've sort of told you like everything that happened at every step of the program. And I guess what I need to I should specify more clear. When a memory cell is read, you also have to specify like the value returned by the read. Okay. Good. So this is this whole execution trace. This is all advice inputs. Okay. Note like if the computer program ran for T steps, you have like order T advice inputs. So it's a huge amount of advice inputs. It is in fact the number of advice inputs is like as big as the runtime of the computer program. So like this this whole circuit is ultimately going to have size like order like T log T or something. So like a pretty big fraction of the circuit is just the advice inputs, right? There's order T advice inputs, and the circuit is going to have size like order T log T. And we actually kind of have ways, depending on, it kind of can get a little tricky what you should call a constant versus a log factor. But we kind of have circuits that are pretty close to order T size, in which case the advice inputs are literally like a constant fraction of the whole circuit. So this is why I said, like a big benefit of GKR-based snarks is the commitment costs for the prover are much lower as long as there are few advice inputs. But in general, front ends that produce small circuits utilize like huge amounts of advice inputs, in which case the benefits of the GKR-based snarks are sort of, not so great. And so, several meetings ago, I discussed that at length, I think. Anyway, so what the circuit will do is essentially just confirm. So, this gets fed into a circuit, and, all of this stuff gets fed into a circuit that will just basically like check that the execution trace is valid. So, like, actually corresponds to the step-by-step execution of the computer program on W, and that, of course, the output is, of the execution trace, of the program, as per the execution trace is 1 or whatever the proof of claims it should be. So that's it. So, and that's the power of advice inputs is the advice can just specify like everything that happened when the prover ran the computer program. And the circuit only needs to check the validity of the advice. It doesn't have to compute the advice from scratch. And so, that's kind of saving the circuit from having to execute the program step by step inside of it. The circuit instead just has to check the validity of the execution trace that was provided to the circuit by the untrusted prover. Okay, so how do you check that the execution trace is valid? So there are sort of two issues, and we've kind of already discussed both of them. So one is called, some of the literature call it time consistency. And this will basically say, trust, just trust for now, trust the reads. So remember, like the execution trace for every read contains the value like returned by the read, right? But remember that it's an untrusted advice input. So like a cheating prover could, say, hey, at step 100 of the computer program, cell 10 was read, and the value stored in cell 10 at that time was, 85, when in fact the value stored at that cell was really, 72. So, we're going to trust that the prover is not playing a game like that. So the trust that the reads actually all return the proper values like stored in the red cell. Time consistency just checks that, given that the reads are all kind of done correctly, each instruction at each time step is executed correctly. So it's basically time consistency is just checking everything but the reads. Okay, and then the other thing to be checked is the reads, and people will call that memory consistency. And so memory consistency means like, every time the computer program went and read a certain memory cell, memory consistency means the value returned by the read in the execution trace provided by the untrusted prover is indeed the value that was last written to that memory cell by the computer program. So that is, you're thinking of the prover itself as kind of maintaining this untrusted memory. And memory consistency means like every time the read is done, like this untrusted memory, which is really like the prover, returns the value that should be returned, namely the last value that was written to that particular memory cell. Okay, questions about this? Now, time consistency is exactly the hand wavy stuff we got into before about simple logic implementing one step of the CPU. And like I said, we do have ways. If you're very naive about it, what you would do is you would literally like implement at each step of the CPU. You would implement every possible instruction in the instruction set architecture. And then just have some, based on the value of the program counter at that time, which is like provided in the execution trace, you just have like a big mux, like a big case statement that tells you like which instruction to actually pay attention to. I guess the picture, it would be, like here you have a circuit implementing like instruction 1, another little circuit implementing instruction 2, and so forth. And, the value of the program counter, which is part of the execution trace, would tell you, let's say there are k instructions. So the program counter would, have log k bits, or maybe it's a single field element storing a number between 1 and k or something. Let's just say it's log k bits, called program counter. And, each instruction would spit something out, but, you would kind of have, with each output, you would sort of take the end, or, I don't know, you could end it with, testing equality of the program counter, and I, if I is, we're dealing with the ith instruction. And then you could just have like an addition gate that sums up the results. And the point is, only for one instruction will the program counter actually equal that instruction's identifier I. And so, taking the sum of all these things, ended with the appropriate equality function. The equality function kills everything but the one instruction you actually wanted to execute at that step. So summing them all up is just summing a bunch of zeros and like what you actually want to pay attention to. So if instruction K got executed, it'd be the only one where the end with the equality, spits out 1 or spits out the output of the instruction. And so the sum will just sort of pick that out, again, hand wavy all the whole way through front ends, but I hope the main ideas are coming through. So that would be, the most naive way to implement like the check time consistency. But there are, it's known now that you can basically kind of only pay for the instruction that actually gets executed at that step instead of paying for all possible instructions at each step in terms of circuit size. It's a little hard to explain how these techniques work. I think there's a paper called VRAM, which I think is the first to really achieve this property, but now it's kind of standard that there are ways to do this. If you ever look at like any of the front ends out there that support a virtual machine architecture, they really, all of them avoid this naive stuff because it's just like untenably expensive. But I do think the first paper that really did this was VRAM. And basically what they did, I can sketch that, I think, in a sentence, is okay, what I'm about to say might make a little more sense in a few minutes, but they would take the execution trace and they would kind of resort it. So they would have even more advice inputs, which is supposed to be the execution trace, but sorted not by time, but by instruction. So that like every time step at which instruction K got executed would be grouped together. Okay, and in that way, so they would kind of have part of the circuit that just like repeatedly like applies instruction 1 and only instruction 1. To all of the time steps that instruction 1 was actually executed. And then the next part of the circuit would imply instruction 2 and only instruction 2 to all of the time steps at which instruction 2 is executed, and so on and so forth. And this can, in VRAM, for this to work, I know I'm being incredibly hand-wavy, but the prover would have to tell the verifier the account for each instruction. That count being, if the prover's honest, the number of times the instruction got executed over the course of the program's execution. So the cost to the verifier would grow with the number of instructions, but like all of these ZKVMs have that issue anyway, that the cost to the verifier grow with the number of instructions. And so basically, if the verifier knew for each instruction how many times it got executed in the program, and then it was also able to sort of the circuit was able to verify that kind of the group by was done correctly, where indeed the execution trace kind of got reordered so that everything, every time step at which instruction 1 was executed got sort of grouped together, and every time step at which instruction 2 was executed got grouped together. Once you have all that information, you no longer have to execute every instruction every time step. Everything that got grouped into like instruction 1's group, you only have to execute instruction 1 because it's in instruction 1's group. And this is the case for each and every instruction. So that's sort of a very hand-wavy and high-level way to see like that. In principle, it shouldn't be necessary inside the circuit to kind of evaluate every possible instruction at every step. You should be able to sort of, with a little help from the prover, telling the verifier something like a count, and then doing a resorting, group by instruction, or again, the ZKVMs today don't do other stuff. Don't do the VRAM technique, but that it shouldn't actually fundamentally be necessary to pay this overhead of executing every instruction every step of the program when post hoc only one instruction was executed at each step of the program. Okay, so that
I have a quick question.
Yeah,
would this kind of technique also still be used in that like lookup singularity example that you gave before, where like everything's just a big table glued together? Or would you need advice in this kind of memory checking in that scenario?
Yeah, I think with the lookup singularity approach, where every instruction is just a lookup into some big lookup table. What we're doing is we are using a small amount of advice and a small amount of logic at each step of the computer program to figure out what instruction should be executed, and then executing the instruction with a lookup. So because executing each instruction is just a lookup, it's sort of automatically getting rid of this issue of kind of paying to execute every instruction at each step. I don't want to say this. So this lookup singularity just sort of, by its very nature, gets rid of this overhead. It's pretty easy to, it's not many gates of a circuit required to figure out what instruction should be executed each step. And then, there's just one lookup at that point. A bad situation would have been if you had to kind of look up the value, if there are 100 instructions. It'd be bad if you had to do 100 lookups to sort of figure out what would be the output of the instruction at that step, kind of without knowing which instruction should be executed. So that'd be bad. It'd be bad to do 100 lookups for every step if there are 100 instructions. We only do one lookup for every step. It is annoying to have this logic that figures out at each step what instruction should be executed. But basically, what's happening is the instruction that gets executed at that step sort of gets the instruction to execute. Right. So you figure out what instruction should be executed, and let's say the inputs to the instruction are X and Y, and these all go into the lookup. And so you do one lookup and that will the lookup will return, this particular instruction evaluated at XY. So what I'm babbling about, I'm trying to get at, you only do one lookup because the lookup itself, like the value looked up, kind of has the instruction that should be executed at that step inside it. And so, kind of the cost to execute every instruction at every step is sort of baked into, the lookup table itself, but no one ever has to materialize that whole lookup table. They only pay for the things actually accessed in the lookups. And so because only at each step, only one instruction is actually executed, everything's good. That was a horrible answer, but I hope it was better than nothing anyway.
No, that definitely helped. I think it's starting to come together slowly for me, but thank you.
Yeah, thanks for the question. I wish I had knew how to be less hand-wavy about this stuff. It's actually going to be a problem. We're still writing up the paper, and I think it's hard to be precise. Specifying forget the circuit implementing a virtual machine, like even just specifying a full virtual machine and like full formality seems pretty nasty, to be honest. Then you try to turn it into a non-deterministic circuit, meaning a circuit taking in device inputs, and it gets even, it's just even worse. Okay, so that is time consistency. Now we get to memory consistency. Okay, so the way people do this now is essentially they will resort the execution trace, but group by memory cell. Okay, so in that, and then for a given memory cell, they will, sort by time. So that way, let's say you sort of, let's say for memory cell I, they'll group things. So they'll have like the initial value of I, of memory cell I come first. And then, if the next time cell I was read or written was at time step 10, that what will come next, for that cell, that cell's group will be, let's say at time step 10, cell I was read. So read of cell I at time step 10, and like the value returned by that. And let's say the next time cell I was accessed was at time step, 25, and there a value was written to cell I. So that'll come next in cell I's group. So value, written to cell I at time step 10. Sorry, I said 25. Time step 25 would be the next time. So you sort of sort things, the original execution trace was in order of time. So, what happened at time 1, what happened at time 2, what happened at time 3. Now we have it in order of what memory cell was accessed in that time step. And within a memory cell's group, we have things sorted by time. And once you do that sorting, it's pretty easy to check that, for every read, the value returned by that read was indeed the last value written to that cell. So, you just kind of look at the, previous step, and you look at the value involved there, and you just confirm that they're equal for each read. So any read, there's some value, and you just test the quality of that value with the value in the preceding, time. So if there's another read here, read to cell I at time, 86, and the return value, you would check a quality of that value and the last value, the value involved in the previous read or write. You would just always confirm a quality every time. And you don't do any checks for the writes, of course, because, if you write a value at a given time step, it doesn't matter what was already stored there because you're overwriting it. And so there's sort of what I haven't told you that you have to check, or how to check it is, so how to check the sorting was done correctly. That's kind of the key issue that I haven't told you yet. All right, and it's pretty late, so I'll this will be the last thing I talk about, I think, and I'll give a brief sketch of how this evolved over time. Okay, so initially people were using something called permutation networks or sorting networks. Okay. I guess it's not really in the book. I actually go into a good amount of detail about what these are, but that's sort of a historical relic. You don't need to know anything about this. So all I'll say is these came out of the PCP literature, and I think people explored them only because. Okay, so you need to use these if you want what I call a non-interactive, and like information theoretic reduction. From running the computer program psi to circuit set. Okay, so as we'll see shortly, in terms of what people do today. What they do is either interactive. It's an interactive reduction. I'll explain what that means shortly. It can then be rendered non-interactive using fiat Shamir, or it's a computational reduction, meaning if the prover could break a crypto system, it could generate a circuit sat instance for which it does know a satisfying assignment, even though it doesn't know a witness that the computer program accepts. So yeah, let me just put my phone on do not disturb. So that I think that's all you need to know about permutation networks. If you're reading old papers, you might encounter these, but I don't think there's any reason to use them today. They came up in the PCP literature because PCPs really do need non-interactive information theoretic reductions, but SNARKs don't, right? Because if it's interactive, you can make it non-interactive with fiat Shamir. And if it's computationally secure rather than information theoretically secure, well, who cares? Because a SNARK by its very nature is only computationally secure anyway. Okay, so the next thing people looked at was Merkle trees. Okay, so basically, rather than doing this resorting, actually they just skipped the sorting. So I shouldn't have put this under how to sort. This is how to just avoid sorting completely. So with Merkle trees, every read would have to be accompanied by a Merkle authentication path, and every write would have to be accompanied by updating a Merkle root. So you need the computer program over the course of its execution. You can kind of think of it as you're modifying the computer program itself, if you want, before you turn it into a circuit, so that it's maintaining a Merkle commitment to the contents of memory at all time steps. Okay, and then every read, it can be self-authenticating by kind of materializing the Merkle authentication path associated with that read to kind of reveal, that leaf node corresponding to that red memory cell of the Merkle tree. And in that way, you're kind of turning the memory into a trusted memory from the start. The computer program itself, you're making it not trust its own memory. You're making it authenticate every read as it goes. And so at that point, it's okay for an untrusted prover to maintain this untrusted memory because the computer program itself was already validating memory as it went by maintaining the Merkle root of memory, and making sure every read was associated with the corresponding Merkle authentication path. And so this is kind of a computationally secure reduction in the sense that, if the prover could break the binding property of Merkle trees, it could produce what looks like a valid execution trace that the circuit accepts, even though it, in fact, is not a valid execution trace. Okay, questions about that one? Okay, so this is pretty expensive in general. This is reasonable for algorithms that just don't do many reads. So reasonable if few reads. So basically, you need the circuit is, verifying Merkle authentication paths in a circuit is not great. This is really, one reason why people have invented SNARK friendly hash functions. Those are hash functions that can be efficiently implemented in a circuit. And it's still not great to do a lot of hashes in a circuit. And moreover, there's logarithmically many of these hash evaluations provided in each authentication path. So each read is really, you're paying a big price in circuit size for each read if you do the Merkle tree approach. So people generally avoid that now. So what they do now is fingerprinting techniques. So So, and this is what I view these as an interactive reduction from executing the computer program to circuit set. Okay, I'm just gonna, well, I'm just gonna sketch this, I think, because it's kind of late. I don't want to, wind up. Yeah, I normally take 2 hours anyway, but it's kind of late to go. This is really important, so I don't want to cover it, this late. I'm just gonna sketch it, and we'll see details next time. Okay, so let me just high level explain how this works. So basically, remember the circuit, is going to look like the following. You got the witness, you got the execution trace, purported execution trace. It's untrusted. It's sorted by time. So everything that happened at step 1 of the CPU, everything that happened at step 2, everything that happened at step 3, so sorted by time. Now you have the execution trace again, but kind of sorted by memory cell, and within each memory cell's group sorted by time. Okay, and what we need to do is we sort of need to check that these two things are permutations of each other. So check that these are the same trace, but just reordered. Okay. All right, so I'm just going to explain this at a very high level. So what's going to happen is the following. Okay, so we're going to have the prover, in practice, the prover would, in a snark, would cryptographically commit to this whole thing. Okay, and then after the prover commits to it, we're going to run a randomized algorithm, to check that these things are the same trace, just resorted. Okay, and we had the prover commit first, because if the prover knew the randomness used by the randomized algorithm when it determined the execution traces, it could trivially choose execution traces that are not resortings of each other, that nonetheless pass the randomized algorithm's checks. Okay, so but once the prover commits to these two execution traces, right, it can't, if only then it learns the randomness used by the randomized algorithm, it can't change what it committed to. So it's okay that it now knows that randomness. You need the prover to learn the randomness of the randomized algorithm, because the prover has to prove that it correctly evaluated the circuit. And so if the circuit itself is executing the randomized algorithm, the prover has to know the randomness used by the randomized algorithm to evaluate the circuit. So yeah, after the prover commits to all this stuff, then you pick. It turns out the randomized algorithm only needs one random field element R. Okay, and then what the circuit will do conceptually is just run the randomized algorithm to do the check that these two things are permutations of each other using randomness R. Okay, that's it. All right. Yeah, what this check will do is actually, we've seen, like fingerprinting. That was the first technical thing we covered in this reading group. And fingerprinting was it was a randomized algorithm to check whether two giant vectors are equal. Now we don't want to check that they're literally the same vector. We want to check that they're the same vector up to reordering. Okay, so what we're going to do is we're going to modify the fingerprinting procedure we've already seen, but to be permutation independent. So that is, if the fingerprint of a vector will not depend on the order of the entries of the vector. It will only depend on the contents of the vector in an unordered, view of it. So it'll kind of view the vector as like a multiset. And so it'll really be like a fingerprint of a multiset. I'll tell you next time what the fingerprinting procedure is, but it's something that can be evaluated very efficiently inside a circuit. It's it's a linear time fingerprinting procedure where all it does is to evaluate it. You wind up, it's just additions and multiplications, and not surprisingly, it's based on low degree polynomials. And so we'll see it next time. Maybe many of you have already seen it, and it's so that is what people do today, and the way I just, you can either think of it, I describe it as interactive because you think of the prover as like, committing to, the execution trace in the two orders, then the verifier choosing R to make sure R really is random, and then the prover evaluating the circuit with R as one of the inputs to the circuit. But if you apply fiat Shamir, the prover itself can choose R. It's just the R will be chosen by hashing the commitment to these two execution traces and the witness W. So that's my view, that this is just an interactive reduction from program execution to circuit set. I think there's a bunch of I wish more people viewed it this way. Firstly, a lot of people attribute this technique to Planck, and it's not. Actually, this sort of thing dates back to something called offline memory checking, which goes at least back to a paper of Blum et al. In the early 90s, and a paper of Lipton even before in 89. And even in the SNARK literature, it was used in VRAM, which predated Planck. So, I've been, I've seen comments like, oh, well, what people do in practice with Planck and Planckish is, they have these like randomized, Planckish instances or randomized errors, and so anyone who puts out like a new SNARK should really express it in the generality of dealing with randomized circuits, randomized errors. And I think that's a little confused. Like you don't have to give a SNARK for like randomized circuits. Just give a SNARK for circuit sat. Like no, there's no randomness, and the randomness is just coming in the reduction to circuit sat. So ultimately, what you apply the SNARK to is a circuit, whose entire input has been, committed to or fixed. So there is no randomness anymore. The randomness was coming in the reduction to the circuit, and ultimately is going to be obtained by fiat Shamir. So I think that this view of, these, randomized permutation checks via fingerprinting as an interactive reduction to circuit sat to enable these circuits to execute a randomized algorithm without suffering catastrophic security loss due to the prover knowing the randomness that's going to be used by the randomized algorithm. Like it should just be viewed as happening in the front end instead of needing to give backends that are described in the context of randomized circuits. Okay, so just a little more of a rant than anything, but I feel like the rants, people seem to like them, I guess. So, all right, so that's everything for today. So next time I'll tell you details of these randomized like permutation checking. So just a few more details. We covered really almost all of it, but so we'll start with that, and then we'll do lookup arguments. And lookup arguments is a pretty substantial topic, so I expect to spend a couple weeks on it, but we might it might be 1 week and then move to something else and then come back to lookup arguments again, depending on I'd like to tell you about this new lookup argument I have and just the perspective that underlies it, and unfortunately I just have to wait until it's ready. So thanks for, as always, staying to the bitter end. If you have some questions, I can stick around for another few minutes. Otherwise, I will see you next week.
I have a super quick question. The offline memory checking paper that you're talking about, or I guess what's the best paper to kind of read about that? I know it was cited in Spartan, I think, but like that paper was like behind a paywall. I'm like wondering if is VRAM like a good paper to kind of read about offline memory checking?
Yeah, I think VRAM might not be bad. I'd say when my new paper comes out, I put a lot of effort into explaining it in that paper, so that will be good then. But I think probably VRAM would be nice now. I can try to get a copy of the old Blum et al. Paper and just post it, in the Discord. I think that's fair use. But it is I think it needs a good exposition. It's very simple, but like somehow hard to explain. So I'm trying to do a good job of that in the upcoming paper. And another thing about this offline memory checking, like not only is this used everywhere today to literally to do memory checking, meaning what I was checking memory consistency of an execution trace in a ZKVM, but it also underlies, like you said, it's in Spartan, so it also underlies sparse polynomial commitments, which I think are really important, and I'm hoping become recognized as such, and this new lookup argument. It's all boils down to this offline memory checking. So I think it is worth trying to understand. Let's say that. So take a look at VRAM. I don't know for sure that it's like a great source for it because I haven't read the paper in a while. But VRAM in general is a pretty nice paper, so it's not going to hurt. And I'll try to get the old Blumedall paper into the Discord, and we'll go from there.
Okay, great. Thanks.
Yeah, and I'll try to explain it like next session, I think, too. So that will probably go poorly, but I'll do my best. So.
Yeah, I think I've actually like read like a couple explanations, and I just hasn't stuck yet. But I think I need to just keep trying. So I'm gonna hopefully by next session I'll have a better understanding.
Okay, sounds great. Any other questions?
Justin, I have one very basic. I just want to make sure I understand the earlier explanation on how to go from like an arithmetic just like a computer program to an arithmetic circuit, and I'm thinking about like SIRCOM. I think they only allow like multiplications in it, but essentially is that all that it's doing? Is just going like step by step with what you did. It's saying, oh, okay, there's a multiplication here, add a node. Like it's just literally building the circuit in that manner.
Yeah, I think it is. So I haven't written in SIRCOM myself. It's kind of embarrassing, but my understanding is it is such a low level DSL that it is almost as if the developer is like specifying the circuit gate by gate. So it's certainly, I would not consider it as like supporting like a virtual machine abstraction. It's just, people call it a DSL, but it's just like so low level. I think that you're really just programming the circuit gate by gate, but kind of by hand. Does that make sense?
Yeah, and maybe some background on my project. So I'm trying, like, I find obviously coding in SIRCOM or a DSL significantly easier than this Halo 2 like execution trace cell relation kind of approach. So I'm trying to take what's in my SIRCOM circuits and like use them on a more performant prover, i.e. like again Plonky 2. So figuring out how to do that is been my roadblock right now.
Yeah. The issue is, I guess, these Plonkish circuits or constraints, like they're more expressive, but they're also just like harder to program or harder to like learn how to program. It's like some kind of weird way of thinking, which by the way is like, there's a lot. It's been hard, like I think like just talking to people who are adept at like programming Plonkish about like CCS, because we just like think about Plonkish in a different way than one does. I think if one's been like in the weeds programming it, like writing Plonkish circuits for a long time. It's just a very specific way of, and like idiosyncratic way of thinking about things and talking about things. So, I don't actually view Halo 2 as like, more or less low. I think it's like roughly the same level of, high or low level as SIRCOM. It's just like a more idiosyncratic kind of constraint system. Let's see.
Well, SIRCOM's super easy. You can just almost code anything that you want. There's this nice. Sorry, and I'm echoey. It might be me, but there's this nice paper. I think I put it in presentation. I put it in the Discord talking about what each DSL can do, and Circom covers most of the categories. Um, so, and as I mentioned earlier, I'm just trying to pick my stack, and if it makes more sense to try to learn this Halo 2 because in Plonkish, maybe that's a road that I need to go down because it seems like it's more aligned with like the level of nitty gritty, for lack of a better word, that a lot of the ZK programming is kind of expected to be in, as opposed to just restricting myself to Circom.
Right. So I think there are two things at play here. Okay, so there's like how big is the circuit going to be? Because like Plonkish people consider to be more expressive than. By the way, Bellman is R1CS. Circom spit out R1CS or just literally arithmetic circuit?
R1CS.
Okay. All right. Okay. So people consider Plonkish to be more expressive than R1CS. And they say, well, academics like R1CS and industry likes Plonkish, and the academics like don't know what they're talking about or something. I am skeptical. I think they really are incomparable. I think the like unbounded fan-in addition gates, essentially, that that R1CS has, can be extremely valuable in certain contexts. And I think you
got it.
Let me. So yeah, I don't necessarily most people out there practicing today are going to disagree with me and say like Plonkish is where it's at. It's just as more expressive and the circuits are smaller. Okay, anyway, so that's one issue. Is I'm a little skeptical. Like you need Plonkish is necessarily better than R1CS. Then there's the question of what backend can you sort of apply to your Plonkish or R1CS that comes out. Okay, and I do think that the existing backends for R1CS tend to be slower for the prover, so they're basically Marlin and Growth 16. The faster one would be Spartan, but that code base today uses a polynomial commitment scheme with big proofs. So that's probably, you'd want to change that in most applications. All of the stuff, using like Fry, so you can work over like a smaller field and things like that. Just currently, I don't believe are implemented for R1CS. So because of the existing tooling, you are sort of stuck with, I guess Plonkish Plonkish or Air, as far as I can tell, if you want to use a Stark backend, even though like the whole point of Aurora and Fractal was kind of to give Starks for R1CS rather than for Air or whatever.
Got it.
It's just the cooling isn't there. So yeah, I guess if you want Starks and you listen to the practitioners out there today, you want to go through Plonkish, and so you want to use that. Now Halo 2 doesn't have a Stark backend, basically because its polynomial commitment schemes are KZG and IPA bulletproofs and not Fry. But it is like a nicely engineered, backend for Plonkish. So yeah, I don't know. That's my rambling. I agree with you that if you use Circom and it does R1CS, I think your options are basically as a backend are Marlin, Growth 16, or Spartan. And if you don't want those backends, I guess you kind of can't go through Circom based on today's tooling, is my sense.
Yeah, and I mentioned this previously. I'm working on the Polygon team, and this is more like a personal project. So like I can ask around like Brendan and Jordy and these guys and like Jose, and because I think part of the ZK EVM rollup has some Circom compiled into PIL, and then the PIL is the language that is then used in a Stark implement. It translates into what they call E-Air, which is specific for the ZK EVM, and then the E-Air is what's obviously used with like the Plonky 2 / like Stark prover. So they're doing a step in there where they're writing one of the verification circuits in Circom, translating it into PIL, and then using PIL to go into E-Air. So I'm kind of getting into the depths here, but what I'm ultimately trying to do is not like have like a much more simple, repeatable process than
Mhm.
going through like a pill to an to air to a Stark.
Yeah. So I mean, if you go through Circom, like you're going to have something that runs and that is
Right.
like somewhat reasonable. By using Spartan or Grow 16 or Marlin as your back end. So I think you have to decide like just how performative you want it. I'm like really optimistic that like what you're butting your head against right now will change like soon, but it's not going to be tomorrow, and so I don't think you should sit around waiting for it to change.
Mm-hmm.
So yeah, I don't know. Those are my best thoughts. Do keep in mind that I'm not out there using this tooling. I just like ask people every time I have the chance, like who do use it, like to explain to me the current situation and how they think of things. But yeah, that's my current impressions.
Super appreciative of this, and yeah, I need to just start shipping some stuff. So to your point, I might start with the pill and see how far that gets me.
Okay, sounds good. I'd be happy to hear how it goes. Yeah, that'll help. You're very much not alone in encountering these things. So,
Thank you, and once again, I really appreciate it. This has been amazing.
of course, yeah.
Yeah.
Thanks so much.
Mm-hmm. Bye.
Bye.